Okay, great. I'll be talking today about confounding robust policy evaluation in infinite horizon offline reinforcement learning. So the motivation of this work is going to be the studying of offline reinforcement learning, and you can think about this as infinite horizon longitudinal causal inference. And some aspects of this problem regime, broadly speaking, are that we don't know the underlying dynamics of the system. In reinforcement learning terminology, we say that we don't have a perfect simulator. And so that means that many model-based approaches, or correspondingly G computation or other approaches that make functional form assumptions, can lead to biased estimation. And secondly, this is a very offline situation where we're doing causal inference with observational data, because running online experiments can be very costly and unsafe, in stark contrast to the rest of reinforcement learning in general, which is about online experimentation. And so there's been a number of recent works that look towards offline reinforcement learning or dynamic treatment regimes in longitudinal causal inference in order to learn optimal sequential treatment policies from this kind of trajectory data collected from individuals over time. And so I'll be talking today about the infinite horizon setting. So this cartoon of patient trajectories just depicts what kind of data set you might be working with in an infinite horizon setting. This y-axis is the patient's glucose state. So we're monitoring it over time in a kind of continuous monitoring setting. And we see some time, we see the time dependence on the x-axis, and you may be working with a series of such patient trajectories that were collected under some kind of observational treatment collection assignment. And so this could be the doctor's decisions, a doctor's decisions, practice as usual. It could be what is called in reinforcement learning under some kind of behavior policy. But we're going to focus specifically on the challenge of unobserved confounding. So there could be additional information or additional unobserved confounding U that informs the historical treatment assignment decision, but is not actually recorded in your data. And this is pretty common. This can be pretty common in healthcare settings because many of the data sets that people work with were really collected for convenience. And so this happens in practice that people use these data sets or these observational data sets. There's this very famous database that was, a lot of people went into a lot of effort to make this publicly available, but it's essentially just the collection of electronic medical records. And so the evidence of efficacy for these policies is essentially exactly based on this kind of statistical evaluation of these kinds of counterfactual means from this observational data, precisely in settings where we know that the assumptions that justify longitudinal causal inference are probably untrue. So that's a kind of broad, high-level motivation. This talk is going to be about obtaining partial identification bounds under a very restricted model. So we're not going to handle the full complexity of these problem settings, but I'm going to provide a very high-level overview of how we can obtain these kinds of robust bounds. So the general idea is that we're going to reason about what it is that we could do if we had access to all of the information, the full information data, and we're going to focus on the kinds of estimation we might do, building on offline reinforcement learning if we had access to all of the information, the observed states and the unobserved confounders. Of course, the challenge is that we don't have access to all of this information. Our observational data sets omits the unobserved confounder. And of course, we can't get something for free in this type of setting. So we're going to have to add additional assumptions. So first of all, we're going to have to impose additional structural restrictions on the underlying latent dynamics that generated the data. And so this will posit a certain kind of graphical restriction or assumption on the unobserved confounding. And we're going to obtain robust bounds by essentially lifting or optimizing over a sensitivity model from causal inference, which the basic logic is about relating what we don't observe, how the actions were obtained conditional on unobserved relative to what it is that we can observe. So the outline of the talk is just going to be about describing these components and telling you how we obtain our bounds. Essentially, at a very high level, about maximizing or minimizing a statistical estimator such that the unobserved components of the statistical estimator are valid probability distributions compatible with their observational distribution and consistent with the additional assumptions that we're imposing here. So for the rest of this talk, I'm first going to go through the problem setup more formally about offline reinforcement learning, introduce the precise structural restrictions we use. I'll walk through the development of this method for obtaining robust bounds by talking about the estimator, the sensitivity model, and then I'll talk about our results, which are more about characterization. So about ensuring validity that we can optimize over these optimization variables and relate that ultimately to the set of MDPs that was generating our observed data. So I'll start with the problem setup. And so I'm going to posit that the data came from what was an infinite horizon Markov decision process on a full information state space, the product space of S and U. So S is the observed state space. It's going to be restricted to be discrete, and U is a space of unobserved confounders, which can be quite general. So the underlying dynamics are a bona fide Markov decision process. We observe trajectories omitting this unobserved confounder information, and it was ergodic on this full information state space. In case anyone is unfamiliar, the decision protocol is simply that at a given full information state S and U, you receive some reward that is dependent only on the observed state. You take an action A in our observational data, depending on both the observed and unobserved confounders. That's where the unobserved confounding comes from. And you transition to the next state, S prime U prime, with some transition probability defined on the full information state space. Now, intuitively, so far I haven't described any restrictions from a normal MDP, except for that the rewards depend only on the observed state. Later on, I'll describe exactly what we are assuming, but you should just think about this as we're going to consider unobserved confounding that is exogenously generated at every time step. So there is no dependence between unobserved confounders at different time steps. And you can think about this a little bit like the reverse of a POMDP. So in a POMDP, you have this hidden state, it emits exogenous observations, and your reward depends on the hidden state. In contrast, in our model, the unobserved confounder affects both actions and the transitions to next states. So transitions are confounded, but it doesn't affect the rewards. And so you don't necessarily want to conduct inference on the hidden state. Okay, so I'm going to introduce some objects that make estimation easier in the infinite horizon setting. So for a fixed time step, T, we're going to define the empirical joint distribution of state action next state frequencies. And so this is just the frequency with which you observe a certain kind of transition tuple. Now, the time limit of these empirical distributions is what yields the stationary state action state occupancy distribution, or the kind of stationary probabilities of observing these transition tuples. Now, when you marginalize these full information occupancy distributions, you can recover what is more familiar as the stationary distribution on the chain induced by some policy pi. So I'm going to call P infinity for some policy pi, the full information state occupancy distribution. And of course, you can further marginalize this to simply the observed states. Now you can define these stationary distributions under the behavior policy and the evaluation policy. So you can pick pi to be E or B. You observe the observed state marginalized distribution under the behavior policy, but of course you don't know it under the evaluation policy. So the target estimand in this infinite horizon setting can be written as an average or an expectation of your rewards with respect to the stationary distribution under the evaluation policy. Now, this is different from the finite horizon setting because a lot of the identification results rely on sequential importance sampling. What's important here is that we have an expectation with respect to one distribution, namely that of the stationary distribution. And so this is the estimation strategy that recent work of Liu et al. 2018 take in the infinite horizon case. And we're going to build on this particular estimation strategy and consider robustness with respect to it. And so this estimation strategy focuses instead on trying to estimate the density ratio, W defined on the full information states, which is simply the density ratio in the stationary distributions. And this is in general a marked improvement from trying to do stepwise importance sampling or so on, which would otherwise incur products of these density ratios for every single time step. So this is the main difference in the stationary or infinite horizon setting. So these statistical estimators typically try to estimate this W density ratio function and then simply evaluate or estimate the policy value by taking averages over the observational stationary distribution, which again, you observe. So to briefly talk about related work, the main difference is that most work on offline policy evaluation or estimating counterfactual means in dynamic treatment regimes assumes sequential ignorability for identification, with the exception of assuming certain kinds of graphical structures that can permit identification under latent variables. And so we are going to focus on establishing partial identification in this very specific model in the infinite horizon setting. There is work, a lot of work on partial identification. A lot of it considers the single time step setting when it comes to these kinds of optimal treatment regimes. And for a very abridged comparison to some related work, mostly from offline reinforcement learning, you can think about this as really focusing on these density ratio improvements. When it comes to handling unobserved confounders in the sequential setting, there are a variety of other kinds of identifying assumptions. So there is a lot of other kind of structure that can be available. You can make model-based assumptions and posit some kind of latent variable model, a prior or a deep latent variable model on the unobserved confounding. Those will come with certain kinds of identification assumptions. You can use proximal inference in a true POMDP. That also will impose some kinds of rank restrictions. And so you can think about this as just adding another complementary set of structural restrictions under which you can obtain partial identification. So to conclude this section about the setup, the structural restrictions, I mentioned that you should think about this intuitively as the exogenous confounders are generated exogenously at every time step. The reason for this is because we are effectively assuming that the density ratio, the full information density ratio, is a function only of the observed state. And of course, a sufficient condition for this to be true is when the unobserved confounders are generated in this way. So I've described the structural restrictions, and now I'll talk a little bit more in detail about the estimation strategy. And what's important is that it has this very simplified dependence on what it is that we don't know about our data, namely the dependence of on the unobserved confounders. So to briefly summarize this estimation approach, there's this very nice development from Liu et al. So if you had sequential unconfoundedness, or if you only had these observed states, the way to think about this is that they provide a conditional moment identifying estimating equation for the density ratio, conditional on the next state. Where this comes from intuitively is that let's start with what we know about a stationary distribution. So a density ratio is a ratio of stationary distributions. The stationary distribution satisfies a system of equations, namely that when you evaluate it against the transition matrix, you again obtain the stationary distribution. Now, in particular, that's a single time step expectation over a transition. And when you unroll this expectation, they do it in this backwards fashion, you can intervene on the action distribution. So you intervene with these importance sampling weights, and that's how you obtain this kind of what is called backwards flow equation. So that's the intuition for how they are able to obtain an estimating equation for the density ratio that most importantly relies on taking an expectation over a single transition that depends on the quantity that we don't know, the inverse probability of taking decisions, which I'm going to call beta for short. So our first characterization is that essentially by construction, we can estimate the density ratio by solving this estimating equation if we knew the true functional form of beta and the observations of unobserved confounders, which of course we don't, but we're going to be robust with respect to those. But this already buys us something because we don't have to solve a conditional moment on both the observed and the unobserved state space. So in a sense, that's essentially why we made these structural restrictions, or you can think about it as if this is true, this is a kind of simplification of estimation as a simpler robust dependence. So I mentioned that this tells us what we could estimate if we knew how the behavior policy was taking actions conditional on observed and unobserved. Of course, we don't know that. And so here's where the kind of very traditional ideas about sensitivity analysis and causal inference come into play, because we've essentially identified an estimator that depends on this unknown probability of taking actions in a very simplified way. We didn't try to recover the relationship between the observed and the unobserved confounder or the functional form. And so these very agnostic assumptions are exactly what the sensitivity model from causal inference is going to parameterize. So the sensitivity model that we use simply provides a convenient parameterization. Because we're optimizing, any linear uncertainty set could be substituted for this. And so we follow the marginal sensitivity model of tan, which bounds the odds ratios of selection into treatment under the full information relative to what you can observe, conditional on only the observed state, uniformly by the sensitivity parameter gamma. And now, because this holds uniformly over functions and over these unknown realizations of U, but without imposing parametric restrictions, this essentially means that when we take this optimization point of view, we're going to obtain these kinds of interval bounds on the value that this optimization variable can take. And when we compute these empirical expectations, we're going to have these pointwise bounds that can vary for every optimization variable corresponding to a data point in our data set. Okay, so what we do is that we study this problem a little more closely, and because we are working with a finite state space, we can actually optimize, or we can reparameterize this optimization over a certain marginalization. So we're going to define this G variable, which is the marginalization of this inverse probability weight with respect to an unknown, but possibly adversarial transition distribution. And we can verify that the same restrictions implied by the previous sensitivity model can equivalently be imposed on this new reparameterized optimization variable. And the most important thing is that the dimensionality of this reparameterization depends only on the size of our problem, on the cardinality of the state space, instead of scaling in the size of my data set. Okay, so to put it all together, what we say is essentially that you can compute these upper and lower bounds by solving what is admittedly a hard non-convex quadratic program. You optimize over these G variables and the estimation variables W. You optimize over the sensitivity model, over the validity requirements that it's an inverse probability distribution, and you optimize over your partially identified estimating equation. So this is a kind of strange, robust bi-level problem. It's generically a non-convex quadratic program. It's bilinear, but when it comes to computation, because we've reparameterized it to depend on the size of the problem, Gurobi can solve this for small instances. And so that's what I'll show you at the end. So I've described the method. I've told you how we put these pieces together. We ultimately write this down as a non-convex quadratic program. And I'll talk a little bit about some of the subtleties in studying sharpness or relating this optimization that we're doing in the space of restrictions on the estimating equation back into ensuring validity for all MDPs compatible with our observational distribution. And so I'll talk about this kind of at a high level, but I said that we want to make sure that we're optimizing over these inverse probability weights that are compatible with the observational distribution. So far, the only thing that I haven't accounted for is that the adversarial behavior policy that I'm optimizing for is stationary with respect to my observed observational stationary distribution. And so essentially what's funny about this problem relative to other sensitivity analysis and causal inference is that if you study what is known in the MDP literature about the valid state action state polytope of occupancy distributions, this is very classical. It's used to study regularity conditions for MDPs. It's that you can't actually enforce this equation. We've added the constraints from the sensitivity model that exhaust the observable implications. Instead, really what is enforcing validity is the combination of the sensitivity model and the estimating equation. So that's a kind of subtle inside baseball note on how this compares to sensitivity analysis and causal inference. Something interesting is that you can be infeasible for small value. You can be infeasible in the setting for values of a sensitivity parameter. So your data can reject the sensitivity model because of these violations of stationarity or compatibility. Okay, so again, when it comes to computation, it's non-convex. I derive like an alternating minimization approach, but there's not much that can be said about it. Because we have this reparameterization, it's actually solvable in practice for very small examples. And when it comes to statistical consistency, so far, everything I've said assumes that we plug in true distributions. Of course, these are estimated from data. You compute the empirical joint distributions. And we show that as the distributions that you plug in converge, so too do these robust bounds. Now, unfortunately, to prove this, we had to, because we were thinking about it as a perturbation analysis of optimization programs, and perturbation analysis of left-hand side constraints is much less quantified relative to other kinds of perturbations. And so this uses a very general variational analysis results, which is just about the stability of optimization problems to perturbations in general. Okay, so I'll describe a very small example just to show what these bounds look like. And so I mentioned that you can solve this with Gurobi for very small instances. And so here's a small instance. We have a small 3x3 windy grid world. You start in a start state. You want to get to the green goal state. Along the way, there are some dangerous red states, and the wind comes into play because with some probability, the wind will blow you into the danger state. Now, an unobserved confounding could arise if you had a forecast of the wind. And so essentially, what this means is that an optimal policy on the full information state space is going to take actions that depend on the unobserved confounder. And so this is a way of introducing unobserved confounding. Now, on the right, we show the bounds. As we go from green to orange, we're trying to evaluate policies that are closer to optimal. So they deviate further from uniform. And so as we go from green to orange, our bounds become more and more ambiguous. They become looser. And this reflects that if we're trying to go further from the distribution that generated the data, there's more ambiguity. And the bounds become looser. And so in general, these robust partial identification bounds, you can think of as they can be quite loose. And so they're either uninformative or they encourage you to collect more data, invest in running a sequential randomized trial, or in good cases, like this green case, they can still be informative decisions because these bounds still bound you uniformly away from zero. And so I'll just conclude there. So again, the goal is to reflect fundamental ambiguity rather than spurious precision. And there are interesting open problems. Inference is really important, but because of all of this non-convexity, it's much harder to establish statistical inference. And there's other interesting questions about sharpness and finite sample trade-offs as usual. Okay, thank you.
There it is. Okay. Hi, Angela. Thank you. This is a very interesting talk. Just a quick question. So you've chosen a particular sensitivity analysis strategy for unobserved confounding. And of course, there are lots of them, right? So you've picked the one by Rosenbaum. There are other likes based on tilting and all sorts of things like that. So is there any particular advantage to picking the one you chose for what you're doing versus other things?
Yeah, that's a great question. There's not a very specific advantage relative to the tilting-based approaches. This is much less about conducting inference or estimating or doing inference under some kind of model of how the U were generated. And so in some sense, most of these results are fairly agnostic to which sensitivity model you choose, so long as it is linearly representable. So convex restrictions on the beta variables are difficult computationally, but linear is fine. So these results are not very specific to which kind of restriction.
So, but you also mentioned that the solver that you end up, you can only do toy problems with this. So is it quite obvious that if I picked a different sensitivity analysis strategy, it would also be similarly intractable? Or might it be that some of them are easier to deal with? It's not clear to me.
That's a great question. This marginalization or the intractability really comes from this nested approach where you want the beta variable to be feasible for the thing you're trying to estimate. So I think a different identification or a different estimation approach in combination with different choices for the sensitivity model would have different tractability implications. So the intractability is introduced much more by the estimation approach that we're building off of rather than the sensitivity model per se. It's just the combination of estimation and the statistical estimation approach.
Okay, got it. Thank you.
Any other chat? I don't think so. No? Okay, then let's thank the speaker again.